students, welcome back. Now in this part I am going to explain you about the theorems that are related to continuity, and there are two main important theorems which are very important according to IIT-JEE point of view. So these two theorems are intermediate value theorem and the extreme value theorem. So now let's see that how these theorems are learned and how these theorems are applied in the problems that are coming in the examinations. So let's start. Alright, so now let's discuss about theorems on continuity. Okay, so let's start with theorem number 1. Theorem 1 says that if fx is continuous and if gx is also continuous, right? So if there are two functions which are continuous functions, right? Fx is also continuous and if gx is also continuous, then fx plus minus gx will also be continuous, f into gx will also be continuous, and f divided by g will also be continuous, provided g is not equal to 0, right? Denominator should not be equal to 0. So just take care of this part, that denominator should not be equal to 0. So if there are two continuous functions, if fx is also continuous and if gx is also continuous, right, then its addition, division, subtraction, multiplication, everything will be continuous, right? If we add the two functions, divide the two functions, subtract the two functions, multiply the two functions, all of them will be continuous only, right? If fx is continuous, gx is continuous, then fx plus gx, fx minus gx, fx into gx, and fx divided by gx will also be continuous. This is the first part. Right. Second part is if fx is continuous but gx is discontinuous. So there is one function which is continuous and there is another function which is a discontinuous function. Right. So if I add one continuous function and a discontinuous function, or if I subtract one continuous function and a discontinuous function, then the resultant will also be a discontinuous function, right? So addition of one continuous and one discontinuous function will be a discontinuous function, right? Also the third part is if fx is continuous and gx is discontinuous. So again the same thing, that if one function is continuous and the another function is discontinuous, then fx into gx and fx divided by gx may be continuous, may be discontinuous, right? It may be continuous, may be discontinuous. Now let us see this through an example, right? Suppose if I take fx is equal to x, fx equal to x is a continuous function, y equal to x, and if I take gx equal to sin x, sin x is also continuous function for all r, right? So this is continuous, gx is also continuous. So if I talk about x plus sin x, which is f plus g, so x plus sin x will also be continuous, x minus sin x will also be continuous, x divided by sin x will also be continuous, and x into sin x will also be continuous. All these functions will be continuous, right? Addition, subtraction, division, multiplication of two continuous function is always a continuous function, right? Remember this first law. Now second is if there is one continuous function and one discontinuous function. Now let for example take this fx equal to x. Now this function is a continuous function, and second example is gx equal to 1 by x. Now this function gx will be discontinuous at x equal to 0, critical point. This will be a discontinuous at x equal to 0, right? So fx is continuous and gx is a discontinuous function. So if I add or subtract, then I will definitely get a discontinuous function, right? So x plus 1 by x or x minus 1 by x, this will definitely be a discontinuous function, because this part is continuous but this part is discontinuous, right? So continuous plus discontinuous or continuous minus discontinuous will always be discontinuous, right? Because one of the part will be discontinuous, right? If in this part I don't have to lift the pen, but in this part I have to lift the pen, and if I add both the graphs, then in fact in the addition of the graphs also I will have to lift the pen. So this will be a discontinuous function, right? So one continuous and one discontinuous, if they are added or subtracted, the resulting will be a discontinuous function. But if we multiply these two functions, right, this is a continuous function and this is a discontinuous function. Now if I multiply f into g, or if I divide, right, multiplication or division is just the inverse multiplication, right? So if I multiply this, I will get x into 1 by x. So f into g will be nothing but 1, x and x will get cancelled, okay? So f into g, so product of two functions is 1, okay? So this is a new function hx which is equal to 1, right? Now hx equal to 1 is a continuous function, right? So if one function is continuous and the other function is discontinuous, then the product may be continuous or it may be discontinuous, right? So nothing can be said about it. Okay, this type of questions are usually asked in assertion region type of question, right? Where one statement is given when one another statement is given, and then they ask you whether statement 1 is true, statement 2 is true, both the statements are true but the explanation is not correct. Okay, both the statements are true but it is statement 2 is an explanation of statement 1, right? This type of questions are framed on the basis of these theorems. Okay, so it is very important for that type of questions, right? So if fx is continuous, right, if both the functions are continuous, then addition, multiplication, division, subtraction, everything will be continuous. If one function is continuous and one function is not continuous, discontinuous, right, then addition and subtraction will be surely discontinuous, but multiplication and division may be continuous, may not be may be continuous, may be discontinuous, right? Nothing can be said about it, so it will be maybe. Okay, now let us study if both the functions are discontinuous. Right, fx is also discontinuous function and gx is also discontinuous function. Then in that case, okay, fx plus minus gx will also be maybe continuous, maybe discontinuous, right? Nothing can be said about this also, and nothing can be said about multiplication and division also, right? Fx into gx and fx divided by gx. Nothing can be said about this, and nothing can be said about this. So f plus minus g will also be maybe continuous or maybe discontinuous, right? And f into g and f divided by g will also be maybe continuous, maybe discontinuous, right? So we cannot surely say anything about both of this. Okay, now let us see this through an example, right? So tell me, think of two discontinuous functions which if I add they become continuous, right? Now a very good example of this can be fx is equal to fx is equal to integral greatest integer of x, and gx is equal to fractional part of x. Right, now this is also a discontinuous function because we know that integral greatest integer of x is, the graph is a steps like function, right? So this is a discontinuous function, and greatest integer of x is also, and fractional part of x is also discontinuous. But if I add them, fx plus gx, then by the property we know that this is nothing but x, greatest integer plus fractional part is nothing but the number, right? So this is nothing but x. So if I add f plus g, I get another function which is just y equal to x. So this will be a continuous function. So if I add two discontinuous functions, then also it is possible that I may get a continuous function, right? So discontinuous plus discontinuous can be continuous. Okay, similarly, discontinuous into discontinuous can be continuous, right? Now let us see this through this example. Now this function is discontinuous at x equal to 0. Because for 0 plus it's 1 and for 0 minus it's minus 1. And this function is also discontinuous at x equal to 0 because for 0 plus it's 1 and for 0 plus it's minus 1 and for 0 minus it's 1, right? So the definition of the function is changing. We have to lift the pen at x equal to 0, right? Now if I multiply this to fx into gx, if I multiply this to, what will I get? Okay, for x greater than equal to 0, I will get 1 into minus 1, so 1 into minus 1 is minus 1, and for x less than 0 also I will get 1 into minus 1, which is again minus 1. So for x, so this will be minus 1 if x is greater than equal to 0, and this will be minus 1 if x is less than 0 also. So this is basically minus 1 for all x, right? It is minus 1 every time for all x, right? So this function is nothing but a constant function which is equal to minus 1, right? So it will be a continuous function, right? So discontinuous plus minus discontinuous can be continuous, and also discontinuous multiplied by discontinuous can be continuous, right? So let us recapitulate whatever we have studied. Okay, let us recall all of this. So if fx is continuous, gx is continuous, then everything will be continuous. Okay, addition, multiplication, division, subtraction, everything will be continuous. If f is continuous and g is discontinuous, so one continuous function and another discontinuous function, then f plus minus g will be surely discontinuous, and f into g and f divided by g may be continuous, may be discontinuous. So nothing can be said surely about f into g and f divided by g. And here, whenever I write f divided by g, g is not equal to 0. Denominator cannot be equal to 0. This always you have to keep in mind, right? Denominator can never be equal to 0. If both the functions are discontinuous, f is also discontinuous, g is also discontinuous, then both the functions will be maybe, right? Maybe continuous, maybe discontinuous, right? Then nothing can be said about anything. Okay, so understood this first theorem. Now let us go to the next part, which is intermediate value theorem, right?
So intermediate value theorem says that if fx is a continuous function, right, this the theorem is valid only for continuous functions, right? If there is a function which is continuous in a closed interval a to b and fa is not equal to fb, then for any value of c which is between fa and fb, there is at least one number x naught in a to b for which f of x naught is equal to c. Right, now this statement is very difficult to understand, but if I give you a graphical representation of this, okay, you will tell me that this I already know, right, because it is such a simple theorem that this is just a common sense, right? See, suppose if this is the graph of a function, right, and if I say that at x equal to a, this is x equal to a, the value of the function is suppose fa, okay, and at x equal to b, somewhere here, this is suppose the point x equal to b, the value of the function is fb, and this function is continuous in this interval a to b. Okay, if this function is continuous in this interval a to b, if I join these 2 points in a continuous manner, right, so that is without lifting the pen, if I want to join these 2 points without lifting the pen, one of the ways can be like this, something like this, right? So this statement says that if fx is continuous on a to b, if fx is continuous in this interval a to b, okay, then there will exist at least one c in this interval fa to fb. Okay, so between these two, there will definitely exist at least one number c. Okay, there will exist a number c for which f of x naught will be equal to c. Right, okay, so for any value c which is between fa and fb, right, so for any value c which is, this c lies between fa and fb, there will exist at least one x naught, okay, corresponding to this c, there will be at least one x naught for which we get the value of the function equal to c. Okay, so if I take any one value between fa and fb, I should get at least one value between this a and b. This is a statement of this theorem, intermediate value theorem, right? It is popularly known as IMVT. Intermediate value theorem, IMVT. Okay? So this statement is clear to you. It says that if a function is continuous in a to b, and if I take any one number between fa and fb, okay, if I take any one number between fa and fb, then for this number there will exist at least one x naught between a and b. For this number c, there will exist at least one x naught in between these two numbers, such that f of x naught is equal to c, such that the value of the function at that particular point is equal to this value c. Okay, now see why I am saying at least one. That means there can be more than one value of x also. I am writing at least one, right? Why I am writing at least one? Because the graph can also be like this. If this is x equal to a, this is x equal to b, suppose. Now I have to join this graph in a continuous manner, right? This is fa and this is fb. So I can join this graph anyhow, but it should without lifting the pen, right? So I can join this graph like this also. This is also a continuous graph, right? So in this case, if I take any one c here, if I take any one value c here, then for this c, how many x will exist between a and b? One will be here, this is suppose x1, one will be this point, this is suppose x2, one will be this point which is x3, right? So there will be three values of x. So f of x1 will also be c, f of x2 will also be c, and f of x3 will also be 3. Okay, that is why in the statement it is clearly mentioned that there will be at least one number, right? At least one number will definitely be there, but there can be more than one values of x also. Right, if I take any one point between, if I take any one point c between this fa and fb, okay, then there will exist at least one value of x between a and b. At least one value of x, right? One value will definitely be there, but it can be more than one also. Like in this case, it's 3. Okay, but at least one value will definitely be there. That is the theorem of IMVT. Okay, we will see the application of this theorem in quite a while. Okay, first let us understand the statement of this theorem. So statement is, if there is some c between fa and fb, then I will definitely get at least one value of x in between a to b, such that f of x naught or f of x1 is equal to c, is equal to that c. Okay, at least one x naught I will definitely get. Okay, now let us go to theorem number 3. This again is a common sense theorem, right? Very simple theorem. Okay, and here this theorem is called extreme value theorem, right? So in the previous theorem we were talking about intermediate values, right? So values in between FA and FB, or values in between, right, somewhere A and B, or between FA and FB. But in extreme value theorem we will talk about the endpoints. Extreme values means either the maximum value or the minimum value, right? So these are the extreme value theorem. So in extreme value theorem, what is the statement? Statement is, if f is a continuous function, this is also applicable for a continuous function on closed interval a to b, right? So that theorem is also for continuous functions. This theorem is also for continuous function. Okay, first and foremost condition for both the theorem is function should be continuous. Otherwise, you cannot apply theorem 2 also, and you cannot apply theorem 3 also. Right? First condition is theorem should be function should be continuous. Then and only then you can apply both this theorem. Right? Now, if fx is continuous on a closed interval a to b, then f takes on a least value of m. Right? The small m is the minimum value, and the greatest value of capital M on this interval. Right? So what this theorem is trying to say is, if fx is continuous function on a to b, right? Suppose this is the xy plane, and suppose this is x equal to a, and at x equal to a the value of the function is fa, and at x equal to b the value of the function is fb. Okay, and in between a to b, in between these 2 points, let me say this point is capital A and this point is capital B. In between these points A and B, the function is continuous. Now we have to join these 2 points in a continuous manner, right? Because f is continuous in closed interval a to b. Okay, then this theorem is saying that no matter how you join these 2 points A and B, there will exist at least one minimum value and there will exist at least one maximum value. Okay, so if I join this A and B in a continuous manner, there will be one minimum value of the function and there will be one maximum value of the function. Okay, so if I join this function like this, suppose, go up and then go down and then like this, right? In this case, minimum value will be here. Here I will get some minimum value which is small m, and in this case maximum value I will get here. So there will be some minimum value and there will be some maximum value. I cannot go up to infinity, right? What this theorem is trying to say is, okay, no matter how high I go, right, I can go on and on and on, but at some point I will have to return. At some point I will have to return, and as soon as I return, this will be my maximum value, right? If I go lower and lower and lower and lower, at some point I will have to return and again go towards b. Okay, because it is a continuous function, right? We cannot break the continuity, right? So we cannot lift the pen, because if it is going up to infinity, that means at infinite we will have to lift the pen, right? But in this case it is said that fx is continuous, so we cannot lift the pen. So at some point we will have to return, right? And where we are returning, there we will get the maximum value, right? So basically, if fx is continuous in between a and b, then it will be bounded. Bounded means it will have some minimum value and it will have some maximum value. Bounded means its range will be fixed. A range will be fixed means it will not go up to infinity, minus infinity or plus infinity in both the directions. Okay, so range is fixed, that is called bounded. Okay, so if fx is continuous, then there will be some maximum value and there will be some minimum value, right? But what will happen if this is the case, right? This is suppose point A again, and this is suppose point B again. If I directly join this, right, A and B, connect by a straight line or some curve like this. Okay, in this case, what will be the minimum value and what will be the maximum value? This is x equal to A and this is x equal to B. In this case, and this is fa, at x equal to a the value of the function is fa, and at x equal to b the value of the function is fb. In this case, what is the minimum value? And in this case also, in between a and b, right, the function is continuous. If the function is continuous in a to b, I said that there should exist some minimum value and some maximum value. Now in this case, the minimum value will be present at point a, right? So this value will be the minimum value of the function. Okay, and this value, okay, here I will get the maximum. So fb is the maximum value of the function. Fb is the maximum value of the function and fa is the minimum value of the function. Okay, so if the function is continuous, there will exist some minimum value and there will exist some maximum value. It cannot go up to infinity. Okay, this is what extreme value theorem is trying to say. Okay, now let us learn about the properties of some some properties of continuous function. So first property is, if fx is continuous on closed interval a to b, then it is bounded, right? Because if it is continuous on closed interval a to b, that means what? Its maximum value will exist, its minimum value will exist. If minimum value exists, maximum value exists, then what will be the range? The range of that function will be from its minimum value to its maximum value, right? So in this case, the range will be fixed, right? Range should not go from minus infinity to infinity. This is the condition for bounded functions, right? Range should not go from minus infinity to infinity, right? So it should not go till minus infinity, and it should not go above till infinity also, right? So range should be some fixed interval on y-axis, right? So in this case, range will be some fixed interval on y-axis, which is from small m to capital M. Okay, so this function is called a bounded function, whose range is a fixed interval. Okay, so if fx is continuous on closed interval a to b, it will be bounded. And second property is, if fa and fb possesses opposite sign, then there exists at least one solution of the equation fx equal to 0 in a to b, provided if f is continuous. Now see, this is a very important property which we will be applying in the questions also, right? What this property is trying to say is, suppose this is my x-axis, right? And on x-axis, this is x equal to a, and this is x equal to b. Now let me consider that fa is negative, and let me consider that fb is positive. Okay, so both of them have opposite signs, right? And y-axis is somewhere here. This is y-axis, right? fa is something negative, so fa will be on the negative side of the y-axis. This is fa, and fb is something which is positive, right? So here, fb, right? Now let me say this point is capital B, this point is capital A, right? And fx is continuous also, see, provided if fx is continuous on closed interval a to b, right? Now if fx is continuous in between a and b, that means I have to join this point capital A and capital B in a continuous manner. Now if I join these 2 points in a continuous manner, okay, no matter how I join these 2 points, right, there are many ways of joining these two, right? One way can be directly join it. Second method can be you can join by like this, then like this, like, okay, there are many ways of joining these 2 points, but in a continuous manner I have to join it, right? So what I am trying to say is, no matter how you join, you will have to cut this x-axis at least one, right? At least once you will have to cut this x-axis. Yes, right? If I want to join this point A and B, I will have to cut x-axis at least once. Why I am saying at least once? Because if I join by this path, let me say this is path 1 and this is path number 2, right? If I join it like this, then I will get this point C1, where f of C1 is equal to 0, right? F of C1 is equal to 0 because y is equal to 0, right? It is lying on the x-axis, okay? Or if I join it by this path, path number 2, then I will get 3 points, right? Here this C2, this point will be C3, and this point will be C4, right? But what I am saying is, there will be at least one point, right? I will have to cut the x-axis at least once, and if I cut x-axis at least once, that means the function will have at least one root in between a and b, okay? Where I cut x-axis, what that point is called? Okay, if I cut x-axis at C1, then this C1 is called the root of the function, right? Because f of C1 is equal to 0. If f of C1 is equal to 0, then C1 is the root of fx. Okay, so what this property is trying to say is, if fx is continuous and fa and fb are of opposite signs, right? It is possible that fa is positive and fb is negative. This is also possible. Fa is positive, but they should be of opposite signs. Okay, if fa and fb are of opposite signs, right? fa and fb possesses opposite signs, then there exists at least one solution. At least one solution means there exists at least one root of fx in between a and b. In between this x equal to a and x equal to b, there will exist at least one root. At least one root means there can be more than one root, but at least one root will definitely be there. Okay, so this is property number 2. Now let's see the application of all this in questions. Example 1, right? Example 1 says that if f be the continuous function defined onto 0 to 1 with range 0 to 1, right? So this function is defined from 0 to 1 2, 0 to 1, right? So codomain and range. So that there is some c in 0 to 1 such that f of c is equal to 1 minus fc, right? Now this type of questions were very common when JEE used to be subjective, right? Nowadays this type of questions are gradually disappearing, okay, but still this type of questions can be asked in SSR region or in some short MCQ type of questions, right? So let us see how to do this kind of proofs, right? So show that. So how do I do this? So what I have to do is, the method for this is take everything to the left hand side in this, right? So this will become fc minus 1 plus c, right? Now replace this c by x and define a new function. So I will define a new function, let gx is equal to fx minus 1. So I am considering some random function gx which is equal to this. Okay, and that random function I got idea, where did I get idea of gx from? I got idea of gx from what I have to prove. Okay, so always keep in mind what you have to prove. Okay, and then define gx according to that only, right? Because ultimately we have to reach here. Okay, so let me define a function gx which is fx minus 1 plus x, right? Now this fx is defined from 0 to 1 to 0 to 1. So range is also 0 to 1, domain is also 0 to 1. Now we have to prove that there is some c in 0 to 1, right? So there will exist some c in 0 to 1. That means this gx will definitely have one root in between 0 to 1, right? Where g of c will become 0, right? So basically in this case, tell me what is g of 0? G of 0 will be f0 minus 1 plus 0, right? So I am not writing this plus 0, f0 minus 1. And what is g of 1? G of 1 will be f of 1 minus 1 plus 1. So this is nothing but f of 1. Minus 1 plus 1 will get cancelled. Now what is the range of fx? See, the range of fx is between 0 to 1, right? So f will always be between 0 to 1, or you can say y, right? Range is basically values of y. So y is nothing but fx. So fx will always be between f of x, you can write, right? Fx will always be between 0 to 1, right? Now see, if fx is between 0 to 1 always, right, what can I say? Then I can say that f of 0 will also be f of 0 will be less than 1, right? Fx will always be for all values of x, right? Whatever be the values of x, okay, fx will always be between 0 to 1 because range is 0 to 1. Alright, so f0 will be less than 1, I can say this, and also I can say that f1 will be greater than 0. Okay, basically f0 will be between 0 to 1 and f1 will be also between 0 to 1. Okay, so I am taking this part from here and I am taking this part from here. Okay, if f0 is less than 1, what can I say about this? If f0 is less than 1, this quantity will be negative. f0 minus 1, right? So if f0 is less than 1, f0 minus 1 will be negative. And if f1 is greater than 0, f1 is greater than 0 means this quantity is positive, right? So from here I can say that g of 0 is a negative quantity, g of 0 is a negative quantity, and g of 1 is a positive quantity, right? Now if I try to see the graph of gx, right, gx is a continuous function because fx is continuous. See, fx is continuous, right, and x minus 1, this is nothing but x minus 1, right? Fx is continuous, x minus 1 is also continuous. So addition of two continuous function is also continuous, theorem 1, right? Continuous function plus continuous function is also continuous. So fx is continuous, minus 1 plus x is continuous, so gx will also be continuous. So first and foremost condition is gx should be continuous. Now if gx is continuous, now try to see the graph. If gx is continuous, suppose this is 0 and this is 1. At x equal to 0, the value is something negative. So somewhere here, right? And at x equal to 1, g of 1 is positive. So somewhere here. Now let me say this point is A, this point is B. Now if I want to join these 2 points in a continuous manner, it will have to cut this x-axis at least once. So let me say where it cuts the x-axis, let me say this point is C. Okay, so for some C, I can say this, for some C in between 0 and 1, for some C in between 0 and 1, I can say that g of C will be 0, and g of C equal to 0 means fc minus 1 plus c equal to 0, and hence proved fc equal to 1 minus c, right? fc equal to 1 minus c, which we have to prove. Okay, understood? So first and foremost condition is assume a function, okay, take everything to the left hand side and assume a function in terms of fx, Now since fx is continuous, this function is also continuous, gx will also be continuous. If gx is continuous, g of 0 is negative, this quantity is positive, right? So at one point I am getting a negative value, at another point I am getting a positive value. If I join these 2 points, I will have to cross x-axis at least once. At least once. Right, so there will be at least one value of c. There can be more value of c again, I am repeating. Okay, let me see example number 2. Example number 2 says that if fx is a, now this is a similar type of example, right? You can pause this video and solve it on your own first, right? If you want it. So same type of example, here also it is said that fx is continuous, okay, in an interval 0 to 1 to r. So a function is defined like this, which is from 0 to 1 and going towards r. So range is full r, right? Such that f of 0 is equal to f of 1. This condition is given in the question, f0 is equal to f1. Prove that there exists a point c in this interval, right? Now we have to prove that c exists in this interval 0 to half, okay, not 0 to 1, it's between 0 to half, such that fc is equal to f of c plus half. Now take everything to the left hand side, so I will get this c plus half. Now assume another function, let gx is equal to fx minus f of x plus half. Now we have to prove that there exists some point c in between 0 to half. So I will find out the value of g of 0 and g of half, not g of 1, right? Because I have to find a point between these two. So find out g of 0 and find out g of half. So g of 0 will be f of 0 minus f of half, and g of half will be g of 1 by 2. This will be nothing but f of 1 by 2 minus f of 1. Now in the question it is given that f of 1 is equal to f of 0. So instead of this I can write f of 0. So this is nothing but f of half minus f of 0. Right? And if I take minus 1 common, okay, so this will be f of 0 minus f of half. Now see, if this quantity is positive, f of 0 minus f half, right, f0 minus f1 by 2, if this quantity is positive, then this quantity will be negative, minus of this, then this quantity will be negative. And if this quantity is negative, then this quantity will be positive. So both have opposite signs, right? If this is positive, this will be negative, and if this is negative, this will be positive. So both will have opposite signs, right? So g0 and g of half have opposite signs. If both have opposite signs, then what can I say? If both have opposite signs, then I can say that there will exist some c between 0 to half such that g of c is equal to 0. And g of c is equal to 0, so we will get the required answer, fc equal to f of c plus half, hence proved. Understood? So simple approach to solving this type of questions. We will assume a function, then we will find out the values, prove that they have opposite signs, and g is continuous, right? Here we forgot to prove that g is continuous. G is continuous, right? You have to prove that also. How will you prove that? Fx is continuous, right? It is given in the question that f is continuous. So this is continuous, this is continuous. So continuous minus continuous will also be continuous. So you have to mention this in the question, if it is a subjective type question, right? So you have to mention this, that this is continuous, so continuous minus continuous is continuous, so g is continuous, and once g is continuous, then you can apply this property, otherwise not. Okay, now in this section we are also going to discuss about the continuity of composite functions, right? Continuity of composite functions. Now first of all, tell me what are composite functions. Composite functions are those functions, okay, for which the output of one function becomes the input of another function, right? Those are called composite functions. You might have learned this in functions, right? So output of one function, right, becomes the input for other functions, such type of functions. So suppose I have function f, right? Here I will give some input and here I will get some output. Similarly, I have another function g, so I will get some output if I give some input. Now if this output of f becomes the input of g, okay, if the output of f becomes the input of g, then we will say that it is a composite function and it will be represented like this, f of gx, okay, or in short you can also write it as f of gx. F of g is nothing but f of gx, right? It is simply a style of writing f of gx, right? And how to find out f of gx? Wherever there is x, just replace it by gx, right? So if I want to find out f of gx, right, wherever there is x, just replace it by gx. So f of gx will be gx plus 1 divided by gx minus 1. Okay, and what is gx? Definition of gx is 1 by x minus 2 plus 1 divided by 1 by x minus 2 minus 1. So from here you can simplify 1 by x minus 2, and this will be 1 minus x plus 2. So this will be x minus 1 and this will be 3 minus x. Okay, so like this you can find out f of gx. Similarly, you can find out g of fx also. What will be g of fx? Wherever there is x, just replace it by fx. So g of fx will be 1 by fx minus, this will be fx minus 2. Wherever there is x, just replace by fx. And what is fx? Fx is given in the question. Fx is x plus 1 divided by x minus 1 minus 2. Now you can just solve this. So you will get x plus 1 minus 2 into x minus 1. Now you can simplify this and find out. So this will be how much? X, so minus x and plus 1 plus 2 plus 3. Right, so this will be g of fx. Right, similarly you can find out f of fx also. So in this replace x by fx. Right, so f of fx will be fx plus 1 divided by fx minus 1, and now you can put the value of fx. And similarly you can find out g of gx. G of gx will be 1 by gx minus 2. Okay, so this is how to find out the composite functions, right? How to find out what is, and this can be also be written as f of g. This also can be written as g of f, g of f. This is f of f, and this is g of g, short forms. Right? In short, it can be written like this also. Now let us try to talk about the continuity or the discontinuity of composite functions. Right? What will be the continuity or the discontinuity of the composite functions? Now first of all, tell me whether this fx is continuous or not. This function fx. This function fx is discontinuous at which point? This is discontinuous at critical point x equal to 1, where denominator goes 0. So this function is discontinuous at x equal to 1, and this function is discontinuous at x equal to 2. Right, so fx is discontinuous at x equal to 1 and gx is discontinuous at x equal to 2. Right, so let me write down here, fx is discontinuous at x equal to 1 and gx is discontinuous at x equal to 2. Now I want to check where f of gx is discontinuous and g of fx is discontinuous. I want to find out the points of discontinuities of f of gx and g of fx. Right, so f of x is discontinuous at x equal to 1. So f of gx will be discontinuous. Again in this statement, just replace x by gx. Right, so f of x is discontinuous at x equal to 1. So f of gx will be discontinuous at which point? At gx equal to 1. Where gx becomes equal to 1, there this point will be discontinuous. Right, and gx will become 1 where? At what value of x? Gx is 1 by x minus 2 and this becomes equal to 1. Okay, so from here you will get x equal to 3. So basically f of gx will be discontinuous at, this is nothing but x equal to 3. And similarly tell me where g of fx will be discontinuous. See, g of x is discontinuous at x equal to 2. So g of fx will be discontinuous where? At fx equal to 2. And fx if equal to 2 will give me how much? Fx equal to 2 means x plus 1 divided by x minus 1 equal to 2, and if you solve this again you will get x equal to 3 only. Okay, again you will get x equal to 3. So like this you can find out the continuity or the discontinuity of composite functions also. Right, so I hope this part is clear to you.
So students, we have seen different theorems on continuity and also we have seen continuity of a composite functions. Now I am going to tell you about differentiability or derivability. Both of these terms are same only. I am going to talk about this in the next part. So do watch the next video.